Hello, my name is Emmanouil Giannakakis, and today I'm going to talk about how different network structures lead to different learning mechanisms. Can you hear me now? Amazing. Okay, so all that. So in neuroscience research, usually when we want to study learning mechanisms, do we? Yes. Okay. So we start with a living tissue, and we prod pre and postsynaptic neuron. Repeatedly, we see, we measure the change in the synaptic strength. And then we develop a model of this, a mathematical formulation of, you have presynaptic activity, you have postsynaptic activity, and sometimes you also model kind of third factor, rewards, or other things. But the focus is usually on what the synaptic changes. And today I want to argue about a more holistic view of learning in living systems, where the learning rules are not by themselves meaningful, but they have to always be viewed in conjunction with the network structure on the network they're acting on, and also the objective functions that they're optimizing. So when something is learned, we have to view the system as a whole, and the interactions between these things matter a lot. So for this, we think of a very simple system. So we think of an environment which has a bunch of ingredients. Each ingredient has some given value, which can be positive or negative. And then these ingredients are combined in different quantities to create food items. So each food item is a vector, and it has a given quantity of different ingredients. So nth ingredient is the nth position in the food vector, and this gives us the quantity of this ingredient. And the total value of the food is the weighted sum of the quantities of ingredients times the values of the ingredients. And if this food value is positive, then the food is kind of good to eat. If negative, is bad. And we create little agents that have to learn this distribution and have to recognize what we eat and what not eat. So we think of little networks which have a bunch of sensors. So each sensor senses one ingredient. So at each step, we present a food item. Each sensor senses its own the quantity of its own ingredient in this food item. And then the agent has a weight vector, which is the internal representation of the ingredient distribution in this agent. And it makes a prediction about what the value of the presented food is. And upon making this prediction, the agent receives as feedback the actual food value. And so it has these three components. So it has the input, which is the food. It has its own prediction of the food value. And then it has the actual feedback of the real food value. So we have three components. And then we iterate through this. The new food is presented. We do it again, et cetera, et cetera. And the goal is to learn the correct distribution of ingredients. And to do this, the weights of the agent, so the internal representation, is evolving according to a synaptic plasticity rule. So this is a classic reward modulated rule, so a three-factor rule. So we have input, which is the X. We have the prediction, which is the Y in this case. And we have the reward or feedback, which is the actual food value. And we take a linear combination of those terms. And what we evolve is the parameterization of this rule. So we have these different components, and we evolve them in order to get as close prediction of the food value as possible. So we use a very simple evolutionary algorithm, and we evolve these 8 terms. And let's see what we get. So our this is our first experiment. The distribution we end up with of the parameters looks like this. So we get all terms go to 0 except for the third and fifth term, which go to about 1 minus 1 respectively. So our rule ends up looking like this, which already makes sort of sense. So you remember from before, we have that the reward looks like this. So we can write our learning rule in this way. So we have a noise term, which we can, okay, nothing we can do there. But on the first part, we have the real weight distribution, and we have the agents weight distribution. So the correct food values and the internal representation. And the fixed point of this is, did it show up? Okay. Why is this happening? Okay, I think there is some, anyway, whatever. Okay. So the fixed point of this equation is the real ingredient distribution. So from this very simple process, we can get a learning rule that is interpretable. So we can see what is happening, and we can analytically show that it converges to the correct ingredient distribution. Now, after that, we thought about modifying the task a little bit to see how different the emerging learning rules would be. So what we thought is that an agent in a real system only needs to know whether it has to eat or not to eat a food item. So it doesn't need to predict exactly its value. It only needs to know whether it eats or doesn't eat. So we can pass the output through a stepwise function. So we make this small change and keep everything else the same. So evolutionary algorithm is the same, what we evolve is the same, loss is the same, everything else. And what we get now with a small change is a learning rule that looks somewhat different. So now, since we have that the y, the prediction is binary, we can write the learning rule like this. So we have, there are two different versions of it. And in general, this can be simplified this way. So we have again, presynaptic activity, and then a reward bounded by something. So in the previous iteration, the reward was bounded by the prediction. Now it's bounded by a different quantity that depends on the prediction, so it depends on the y, but changes. So we have two different learning rules that follow a similar principle, but the details change quite a bit. So if we only looked at the learning mechanism, these would count as different rules. Well, in principle, they do more or less the same thing, but the actual details of the rule change a lot. And the only thing we changed is this single nonlinearity in the neuron. So after this, we thought about how to make the system more complicated. And so we thought about embodying it. So right now we have a single input, which is the food, and we have a single goal, which is to predict either the value or make the decision. And then we thought about making it embodied, so allowing it to move and embedding it in an environment, which would give it much greater freedom to develop different properties. So we now develop a motor network, which moves an agent around, which consists in three parts. So first we have an input layer, which receives information about the closest food. So its distance, angle, and the value of the food. So we have an agent, we have the food distance and angle, and then information about the agent itself. So its speed and its energy, because moving around is costly. This information passes through two hidden layers. And then the output is the linear and rotational acceleration. So this controls how a little creature moves. And the food value, instead of being given directly, is given by the sensor network that we had before. So our original agent is now attached to a motor network. And we're now evolving the connectivity of the motor network, which is static, it's not plastic, plus the plasticity parameters of the sensory network. So these two co-evolve. And we put these things in a 2D environment with periodic, so it has periodic boundaries, and then food particles are distributed around, again, vectors of ingredients. And the idea is the agent consumes food particles by kind of getting close to them, and the fitness is what you consume, the total value of the food you consumed. So the task is solved, like it converges after about 100 generations, and it looks like this. So it does it pretty well. It learns quickly to eat. So the green foods are the good ones. It sometimes makes mistakes, but it's usually pretty good. So we do this, it works, it solves the task. And then let's look at how the evolved rules look like. So again, same parameterization as before, same rule. And now the distribution parameter looks like this. So there is absolutely no pattern. It's a mess. And if we look at the weights it learns, they are also very, very, very much not structured. So there is no correlation with the actual values of the weights. So the question is, why does this happen? So the sensory network would work perfectly well if it was doing what it was doing on the original agents, which is to predict the exact correct value of the foods. But now it actually doesn't need to. What it needs to do is to produce a consistent representation of the distribution. But how this corresponds to the real distribution is completely irrelevant, because the motor network evolves together with the learning rule. And by co-evolving, they can adapt to each other. And so anything that is consistent works for the agent to move around and perfectly do things. And if we mix motor networks and learning rules, then it stops working. So each learning rule is adapted to one motor network. They cannot be interchanged, but they're all perfectly functional. So there is a Pareto front. There is if we optimize too many things, and therefore we can move around in this space and have different rules which work for different networks, and they're all equally functional. And to test this a bit, we thought about creating a bottleneck on the information that the two networks share with each other. So we look at our network again, and the only point of contact is this neuron. So we thought about restricting it as we did before, so making the output their binary. So if we do that, the decision about the food has to be made in the sensory network. So because it can output only 1 or 0. So the motor network, it cannot adapt to anything. It has to do what the sensor network says, because there is no information to interpret. So if we do that and we evolve the rule, it looks like this. So it's still noisy, but now there is structure. And in the reward modulated part, there is quite a bit of structure. So we see that the variance of its term reduces quite a bit. And when we look at the weights that are learned, the correlation now with the actual values is very, very strong. So in this way, we kind of force it to converge to the correct distribution. So if we compare the different rules, we have static and moving networks. So when we have the scalar readout, static is very structured, moving is a complete mess. When we have the binary readout, static is very structured, moving is also very noisy, but we start seeing some structure. And if we limit more things, presumably we will get even more structure. Yep, I'm done. So in summary, when we study learning mechanisms, we can study them properly only if we view them together with the other structures they interact with. So network topology really matters for learning, and local plasticity can only interact with the structures in very specific ways. And if we optimize all those things, so both structure and plasticity, then we get very redundant solutions. So there is a big space solution. And introduction of information bottlenecks can kind of reduce this redundancy. And if these information bottlenecks exist naturally, as is the case in many biological systems, then this kind of may help us for studying them, but also if we introduce them in artificial systems, it can also help in this direction. So yeah, I'd like to thank my supervisor, Levina, and my co-author, Sina. And yeah, questions.